and I think that's it. So let's continue. Right. So what we were doing last week, we were looking at. So we were talking about uplink and downlink. If you remember, we had multi-user communication with multiple antennas. So in the uplink, essentially the strategy, if you have one receiver with multiple receive antennas, and you have multiple transmitters, transmitter 1, transmitter 2, transmitter 3, let's say each of them has one antenna. So this looks like actually kind of some form of spatial multiplexing that we saw in point-to-point MIMO, right? In point-to-point MIMO, we had this, and we had one transmitter where we had this. And then one of the scheme was spatial multiplexing, where we transmit independent streams for each of those antennas here. And so what we were doing at the receiver, we were doing MMSC SIC, right? So here in the uplink, in the multiple access channel, here you can do the same thing. You can have transmit each antennas here, transmit independent streams. So each user transmit independent streams at a power level that is fixed by the maximum power that is allowed by each of those transmitters. And the receiver, what he would do, the best thing he can do is do MMSC SIC. You can do other type of receiver as well. You can do zero forcing. You can do you could do maximum likelihood decoding as well. So all the receiver that we saw for actually point-to-point MIMO could also be used here in this scenario. Right, then we looked at the BC, so the downlink, so that was the uplink. We had the downlink, where we have something like this now. We have a transmitter, and we have multiple receiver. Right, so let's assume again I have single antenna, but I could have multiple antennas. And now I want to deliver multiple streams to those different receivers. Now we have to be very careful here, because if we have multiple transmit antennas or multiple antennas at some of those nodes, this is the strategies are very different from what we do when we have the single antenna case. So the single antenna case, we had this, receiver 1, receiver 2, receiver 3, right? And to solve this, we saw that what we were doing was superposition coding with SIC, right? You remember that. In the multi-antenna setup, doing superposition coding with SIC is clearly suboptimal. What the optimal strategy here is called dirty paper coding, DPC. Right? Now, this is complicated to implement, so in practice, no one has implemented this, but what is often used is some form of linear precoding or multi-user linear precoding. And one of them that I talked about last week that we finished with is called zero forcing beamforming, right? Which is probably the most popular technique, right? So today we're going to continue looking at superposition coding. So in coursework 3, you will see you have some questions. You have 2 bonus questions. Try for you to get some more marks. And you will see that one of the questions relate to this literature. This superposition coding with SIC is also called NOMA, non-orthogonal multiple access. Right, so there is a big literature on doing multi-antenna NOMA. So when you use this idea of superposition coding with SIC, but you apply this in a setup like this one here on the left, right? And so one of the questions there is actually to try to discuss this, whether actually this is a good strategy, and you will have to read one paper or part of a paper that discuss this matter. Good, so let's go back to our zero forcing beamforming. So what do we try to do? Let me write our system model here. Let's imagine that I have a user queue here. And now let's imagine I have those 3 users. So I have Q is one of those 3 users. I have HQ multiplied by a precoder for user Q, multiplied by this stream. And then I'm going to have a sum here over all other precoders plus some noise at user Q, right? So this is the intended signals of user Q. This is actually the multi-user interference that user Q sees, right? So for instance, in Q, if Q is equal to 1, user 1 will see interference from the other co-scheduled users. So we'll see interference from user 2 and user 3. Right. So what we want to do in zero forcing beamforming, we want to make sure that actually this term here goes to 0, right? So we want to make sure that a certain precoder, WP, is always orthogonal to the co-scheduled channels. So the precoder of user 1, for instance, will be orthogonal to the channel of user 2 and user 3. The precoder of user 2 will be orthogonal to the channels of user 1 and user 3, and so on, right? So this is really what we want, and so if you do that, if you do that, then certainly this term is equal to 0, and what you can imagine is that each of those k users will see only this term and a noise. So you will have a transmission that is the same as if you have no multi-user interference. So if we have perfect zero forcing in this scenario here, I'm going to have something like W1 is H1 W1 S1 plus N1. Sorry, W1. Y2 is H2 W2 S2 plus N2, and Y3 is H3 W3 S3. That's what we end up with if you have perfect zero forcing beamforming. So you're really able to satisfy this. Otherwise, if you don't have that, then you're going to have this interference term that will appear at each of those relationships. Right. So how can we do that? How can we design this precoder? Well, I can take my different H. So H I every time vectors here, right? So in this 3 user case, let's imagine that I take H1, H2, and H3. Right. So let me write this slightly differently. So here what you see is that I can write this like this: Y1, Y2, Y3. Right. And this will be equal to something S1, S2, and S3. And I have essentially a diagonal matrix here. There's some noise vector, right? So the diagonal entries here are essentially given by those terms, right? And I have zeros here because essentially I don't see any interference, right? So this is what I want to end up with when I do zero forcing beamforming. I want to end up with a scenario where essentially if I stack all my observation here and all my transmit signal symbols here, essentially I want to have an effective diagonal matrix. That means that the stream will not interfere with each other at the receivers, right? So how can I do that? Well, I can write this this relationship slightly differently here, right? I can say, oops, here, say this is Y1, Y2, Y3, and then I have W1, W2, W3. Those are my precoders multiplied by S1, S2, and S3, my 3 streams, plus some noise vector. Right, so what I would like to do, I would like to make sure that actually this matrix here essentially becomes diagonal, right? So I have to find a W such that this product is diagonal. So how can I do that? If I call this H, for instance, so if I call this matrix this one, let's change color. If I call this H, right? So I can, and this I call, let's say W, or I think I call this F in the lecture notes. So let me take F, right? So how can I do that? Well, I can do exactly the same idea as what we did with the zero forcing receiver. We were forcing the interference to 0. So when we do that, we force the interference to 0. So what I can do here is actually an inverse of this. I have 3 antennas. In this setup here, I have 3 antennas, and I want to force the interference to zeros at 3 receivers. So actually, I can do just an inverse of H, right? Assuming this is invertible. So this would be, here would be a 3x3 matrix, right? This could be a 3x3 matrix. I have 3 transmit antennas and I have 3 receiver, right? More generally speaking, so this is for the 3x3 case. If I have 3 receivers, but I have NT transmit antennas, so I have more antennas than the number of users, what I can do this this generalized inverse, which says I will do, which is exactly the same as what we did for the multi-user, the zero forcing case. I will multiply by Hermitian, and then I will do the inverse. If I do this, if I replace F by this, right, actually this whole matrix here would be diagonal. And so we would force the interference to 0 at each of those receivers, right? Now, there is an important thing here is that F here, you see, is not normalized. So usually I always normalize those columns such that I respect the transmit power constraint, right? So here I have not normalized the columns. So F is not normalized. So what I need to do next, I take the column of F. The column of F would give me the W, and I have to normalize each of those columns in order that such that the norm of W is fixed to a certain value, for instance, equal to 1, so that I can maintain I can control the transmit power across my transmitter. Okay, so that's the idea of zero forcing. You really aim at getting rid of this. Essentially, you transmit every time you transmit a certain precoder, WP would be designed to be in the null space of the matrix given by the co-scheduled channels. Right. So that's in other words what it does. So this works relatively well, but similarly to the zero forcing receivers, you can imagine that this only cares about forcing the interference to 0. It doesn't care about the noise, right? So if you have, for instance, an interference, a multi-user interference here that is already negligible compared to the noise power at each of those receivers, maybe it's not worth to really try to get rid of this multi-user interference. Maybe you could try to instead design your precoders that you maximize the SNR, right? So there are other types of precoders that can be used. Another one is called regularized zero forcing beamforming. So you have a R in top of this here. All this is not in the lecture notes here, but everything is in the book if you're interested. And regularized zero forcing beamforming essentially is a form of MMSC precoder. So it's a precoder that will be designed such that you balance the effect of the multi-user interference and the effect of the noise. And so if your noise is actually very dominant compared to this multi-user interference, you will try to actually maximize the SNR by having your precoder that is more closer to kind of match beamforming. If the interference is actually more dominant, you will evolve towards more something that is like a zero forcing, and in between you will actually balance those two terms. A bit similar to what we did for the MMSC receiver, right? So this is something that exists as well. Right. So, but zero forcing beamforming, the basic one, is actually the most common one. Right, so one important thing here, if you want to do this inverse, you need to have the number of transmit antenna has to be larger than the number of streams that you want to transmit. Otherwise, you actually cannot force the interference to 0. So if you have, let's say, only here, if you have only 2 antennas, for instance, but you have many more users, more than 2, then you will not have enough antennas here in order to actually force the interference to 0 to each of those receivers, right? So the zero forcing beamforming does not work in that scenarios. And then other types of transmission could be used. The DPC would obviously always work, but simply like linear precoding like this would actually give you some issues. Right, so for those who work in their project on, for instance, rate splitting techniques, you will have to implement all this kind of stuff. Obviously, you can do things beyond that. Here, actually, kind of closed form solution to do those precoder design. You can use optimization, convex optimization tools to optimize those precoders as well. Right, so this is essentially what we describe. I describe here. Sorry, here, right? And the normalization. You see, actually, this is not normalized, and the precoders at the end here is equal to the column of H divided by the norm of H that you normalize the precoders for each of those users, and so you can control the power that you're going to allocate exactly to each of those users. Right. So good. So what happens if you do that? So if you do that here, then what you see is that in this scenario, I have 3 transmit antennas and I have 3 users. And I was able to get rid of this multi-user interference. So now I have 3 observations that sees no interference, right? So that means actually user 1 here, user 1 will achieve a rate that is a single user rate that essentially is a log2 1 plus SNR, right? And the SNR will be proportional to, here I'm going to have a log2 1 plus the H1 W1 square divided by the noise power, right? And in my W here, I can have the power allocation that is allocated to user 1. Here I'm going to have also log2 1 plus H2 W2 square given by this, right? Under the condition that those W are designed according to the zero forcing. And then similarly for user 3. So what you see here is that each user will receive 1 interference-free stream, right? So you have 3 users in the system, you have 3 antennas, and essentially you're able to deliver 3 interference-free streams, right? So your sum rate here will write as essentially the rate that is achieved by user 1 plus the rate that is achieved by user 2 plus the rate that is achieved by user 3. So I'm going to have essentially a sum over k of log2 1 plus SNR of each user k, right? I don't have any interference here anymore, right? Because the interference was completely disappeared, essentially. Right? So at high SNR, if this SNR increases, right, this will be roughly equal from 1 to 3. This will be roughly equal to 3 log 2 or 3 log 2 SNR, right? So those SNR for these different users may be slightly different, but what I mean here is that a rough order of magnitude, I'm going to have 3 times log 2 SNR. So in other words, I will be able to transmit 3 interference-free streams in these systems. So this is where the multi-user in MIMO or zero forcing beamforming here is very helpful, is that if you had scheduled only 1 user in this system, so if you were doing single user transmission, you would actually have scheduled user 1 or user 2 or user 3, so 1 user at a time. So for instance, I schedule user 1 at time 1, user 2 at time 2, user 2, 3 at time 3. But you could do actually better than that. By leveraging the multiple antennas you have a transmitter, you're actually able to transmit multiple users at the same time on the same frequency band, right? So this is where you see here, you have now a multiplexing gain, right? And we call it some multiplexing gain. So the number of interference-free stream that you transmit in this system now is equal to 3. And 3 turns out to be the minimum between the number of users that we have and the number of antennas, right? And this is what happens in general. If you have a systems here where you have k users and you have NT transmit antennas, the maximum number of interference-free stream transmit will be equal to the minimum between the number of users and the number of transmit antennas. So this minimum relate to essentially if you have k is much larger than NT, What it means is that you will probably transmit to a subset of those K users, and you will perform zero forcing beamforming across this subset. So if K is equal to 10, for instance, and you have 4 transmit antennas, well, the transmitter, what he will do, he will select out of 10 users, it will select a subset of those users, and then it will perform zero forcing beamforming to that subset of the users, right? And at most, because he has 4 antennas, at most he will be able to transmit 4 interference-free streams, right? So you see, as the dimension of the antennas here increases, it means actually you could accommodate more users. If you have 100 antennas, and you have 100 users, potentially you can actually transmit 100 interference-free streams in the system. So you can really increase the sum rate significantly compared to the performance you would have with some form of time division multiple access, where you transmit at 1 user at a time. Okay, so that's the idea. Going to the large dimensional here, this is the massive MIMO regime that I will talk about later on today. Right. So so in general, this is the expression that you have for your sum rate. You have a sum over a certain number of streams that is at most equal to the minimum between the number of transmit antennas and the number of users of the rate that is achievable by each of those streams. So this is actually now just a SNR. It's an SNR expression here. And I have a certain power allocation here. You can go into this. This is just an SNR expression that you have after the zero forcing beamforming. But so the main message here is that roughly you have indeed a multiplexing gain that or sum rate that scales as the multiplexing gain, the sum multiplexing gain multiplied by the log2 SNR. Right. So this is actually, this quantity, this is the maximum achievable multiplexing gain. So this is the maximum achievable number of interference-free stream you can transmit in the system. So if you use more complicated strategy like DPC, right, the capacity achieving strategy, you will not be able to transmit more interference-free streams. Your rate, your sum rate would be larger, but the number of interference stream that you can transmit will remain the same. Good. So let's move on, and let's look at some performance of zero forcing. So here I have 20 users, and I have 4 transmit antennas. And so, and I have here 2 figures. I have on the left-hand side, I have linear precoding techniques. So one of them is zero forcing. This is zero forcing beamforming, but slightly enhanced. I will talk about this in a minute. And here on the right-hand side, I have non-linear precoding techniques. So actually, those are techniques that do not rely simply on linear precoding. They're a bit more involved. And then one of them is the capacity achieving one is DPC, right? So what you observe here is the following. You have 20 users and 4 transmit antennas. And so the minimum between NT and K is equal to 4. So that means that your sum rate should scale as roughly 4 times log2 SNR, right? So in other words, if you increase, your sum rate will be roughly 4 times log2 SNR. So roughly, if you increase your SNR here by 3 dB, you will gain 4 bits per second per hertz, right? So the slope of this should be equal to 4. You're gonna have to zoom here, but essentially, if you increase here, if you increase by 3 dB, here you should get 4 bits per second per hertz, right? So this is good, right? This is much larger than if you were doing single user transmission or TDMA, where you would have a 1 here, only 1 bits per second per hertz, because you deliver only 1 stream for each of those users. Each user has a single receive antenna. Right, so this is the zero forcing beamforming performance. And so what happens here is actually you have 20 users, so you transmit to a subset of those users. So the transmitter, what it would do typically, it would try to find and pair users together. So find 4 users actually to work well together. So find a subset of users that will maximize the sum rate. And so at every channel realization, it will find the subset of the 4 users that will maximize the sum rate. So the subset of the 4 users would not necessarily be user 1, 2, 3, 4, right? Maybe a user 1, 4, 8, and I don't know, and 19 would be the good user that would maximize the sum rate. But it would have to go over potentially all possible pairs of users, or more than pairs of k tuple or 4 tuple of users, and find out which subset is the best one. So it can be quite computationally intensive at the transmitter side to figure out which users have to be paired together. So what you see here is in black is if you do zero forcing beamforming, but you don't really care about which user you choose, you pick up. So you randomly pair a user together. So randomly choose user 1 with 3 other users, for instance. Then you get that performance. If you do zero forcing beamforming, but you actually choose the pair of user wisely, so out of those 20 users, you choose wisely which user should be paired together to be transmitted, then this is actually doing a joint combination of the precoding and the scheduling. So here it's called a greedy scheduler that we try to really find across all those different possible subset, which subset is the best one for each realization of the channel. And if you do that, you see that your performance increase quite significantly, right? So this is one observation is that if you do zero forcing without user selection, without choosing which user have to be paired with which, then the performance could be degraded, right? But if you actually choose zero forcing beamforming with user selection, then actually is a pretty competitive strategy. Right. So if you go on the right side here, this is dirty paper coding. And you see that here the dirty paper coding gives you the best performance, and you have nonlinear precoding strategies here that achieve very close to it. One of them, this green one, we will not go into all those details, but the green one you see comes quite close to it, and the green one is the same as you have here, right? Which is quite close to what you obtain with just doing greedy zero forcing beamforming. So in other words, the greedy zero forcing beamforming in terms of sum rate would come quite close to the DPC limit. And this is one of the reasons why in practice this kind of strategy is used, is because you can use simple linear precoding, but by combining with user selection, by scheduling and finding and pairing users smartly together, you can achieve a very good performance. Right. Now, so there is a good trade-off between complexity and performance, essentially. Now, we have to keep in mind that all what I talked about here, this does not work. All what I talked about here is when we do this, you need to know H, right? Those H has to be known at the transmitter, right? So in other words, here, when I have my transmitter here, and I have my channel, H1, H2, and H3, I have to assume that H1, H2, and H3 are known at the transmitter. So this is called channel state information at the transmitter in a multi-user setting. We have seen this in the point-to-point single user setting before, but this is in the multi-user setting. And when it's perfectly known, so I have perfect channel state information at the transmitter knows H1, H2, and H3 perfectly at the transmitter, right? So if you do that, then you can achieve good performance here, right? As you can see, you have actually phones that are quite close to DPC. This is one assumption that we assume here in those evaluations. So that's the perfect CSIT. Another assumption that we assume is that it's the same average SNR for all the users, right? So that means that roughly the long-term SNR for each of the users is the same. So that means actually all the users experience the same pass loss and shadowing. In reality, it may not be the case. One user may have actually a pass loss and shadowing that is very different from another user. You can have, I don't know, 10 dB, 15 dB difference between two users. And in that case, you have a disparity of channel strength, and that can lead to some further gap between zero forcing beamforming, even with the user selections and the DPC. And the other thing is that we use a max rate scheduler here. So when we do the greedy one, we only care about maximizing the sum rate. So we don't really care about any form of fairness in the system. So if you use fairness, if you use zero forcing beamforming combined with proportional fair scheduling, what you would do then, you will not maximize, the sum rate, maximize R1 plus R2 plus R3, but instead you will maximize W1 R1 plus W2 R2 plus W3 R3, for instance, right? Where W's here are actually the proportional fair metric. So this would be 1 over the long-term rate of user 1, 1 over the long-term rate of user 2, 1 over the long-term rate of user 3, right? So this is called sum rate maximization. This is called weighted sum rate maximization, where the weight are chosen according to the priority that you want to set for each of those users. And one way of setting those weights in practice is using this proportional fair scheduler. So this is what you will implement in coursework 3, but the main part of coursework 3 will be about single user transmission. So you will transmit multiple streams, but always to one user at a time. But you're going to have to choose which user you transmit to according to the proportional fair scheduler metric. But what could be done, and this is something you could do in one of the two bonus questions, is to, instead of transmitting at one user always, you could transmit to multiple users at the same time, and then do a zero forcing beamforming kind of things. And you could come up with a metric that maximizes a weighted sum rate, where you try to find out which user to pair together according to this proportional fair scheduler. Right? So this actually requires quite a bit of work if you go into this bonus question. But if you do that, you will really understand how the multi-user, multi-antenna communication really work. Good. Right. So what if you don't have? So if you look at weighted sum rate maximization and you take into account some fairness, then you may have also some bigger gaps between DPC and zero forcing beamforming, right? So there the gap may increase. And fairness is very important in practical system, obviously. Right, so what happens now if we don't have that, if we don't have perfect CSIT? Right. Well, if we don't have perfect CSIT, we have a system that is called imperfect CSIT, right, in general, or here is called partial knowledge. So it's also, you can find in the literature, partial CSIT. And so this partial CSIT, where may this come from? Well, you can imagine here, you have to know, if I have this example here, I have two users, I have a base station, I have channel of user 1, channel of user 2. So what I explained in the past is that the transmitter would have to acquire those channel H1 to H2 to the transmitter, right? So in TDD, you would use channel reciprocity. So you transmit pilot on the uplink, you perform channel estimation on the uplink, you get an estimate of the channels on the uplink, and you use this for precoding in the downlink. In FDD, you would use quantization. So you use a code book, similar to what you will do in coursework 3. You will have a code book, you will quantize channels of user 1, channel of user 2, and then the quantized version of those channels will be reported back to the transmitter. So you see that the transmitter may not know perfectly the channel, because of estimation error, channel estimation error, because of quantization error, because you can have mobility. So if the users here move and you have just a few milliseconds delay between the channel estimation and actually the design of the precoder, then you will have a mismatch between the precoder design and the actual channel. So the channels, the precoder will have to be designed based on the channels that is slightly outdated. This is what happens when you have mobility and latency. You could have RF impairments. So for instance, you can have calibration errors between the RF chains, between the uplink and the downlink at the base station. And all those reasons leads to actually scenarios where you have imperfect or partial channel state information in the transmitter. So in that case, you can imagine that because you don't know HQ perfectly, you cannot design WP such that this is equal to 0 because you don't know HQ perfectly. So there is no way you can find a WP such that this term is equal to 0 for all values of HQ. What you could do is the following: if you have a WP that is designed based not on HQ but on HQ hat, right? So your WP here would try to be maybe orthogonal to HQ hat, to the estimate of the channels that you have at the transmitter, but it will not be able to be orthogonal to the channel HQ. So you could have HQ hat WP is equal to 0. This is what you could do. So what you would do then, you would do zero forcing beamforming, but based on the estimated channel, not based on the true channel. So what you would do there, here, you would replace now H by, let's say, H hat, right? So where H hat is not the estimated channel. So you have an estimate of the channels for each of those users. Right, so if you do that, then the performance degrades. And the reason why it degrades is the following, is that now this term here is non-zero. And because it's non-zero, this term may be non-negligible compared to the noise here. And because of that, essentially, you don't have a log2 1 plus SNR, but you have a log2 1 plus SINR. So you have an interference term that is left there, and this interference term can be really non-negligible. If it's non-negligible, it means that you really enter an interference limited regime. The interference is the limiting factor in the system. And this is typically what happens if you take a system like 4G, and you have the same in 5G as well. You can have something like this. So this is an example here where you have the sum rate using zero forcing beamforming. You have here 10 users, right? You have 4 transmit antennas. Forget about this. This is a transmit correlation that we have, but that's not very important here. And here you have a certain number of bits. So forget also about the different code books here, but different number of bits. So what that means is that b equal to 4 means that I have actually 16 vectors, 2 to the 4. I have 2 to the 4 vectors. So 16 vectors that I use to quantize the channels of each users. Right? This is typically what you would use in 4G. So you have essentially a code book like you do in single user transmission, and you have a code book or you have a limited feedback, right? You will use this in coursework 3, and so you use you find which vector among those 16 vectors, which one is the one that actually is the closest to the channel, to the direction of the channels, and you report the index of that vector back to the transmitter. And so what the transmitter does is perform zero forcing beamforming, but based on this this estimated channel that is actually based on this one of those 16 vectors. And so what you see here is that you're not able to get rid of the multi-user interference. You will you're not able to have actually a sum rate that keeps increasing. Here you have a sum rate that now saturates pretty quickly. And the reason for this drop here is because now we have an interference term that is left, and this interference is actually quite dominant compared to the noise. As you increase the SNR, the noise power here decreases, but the interference term is still there, and that limits the SINR and therefore limit the rate. Right. So this is a typical problem that you have in 4G. In 5G, similar issues occurs, but they have changed the design of the feedback so that you have more accuracy. So you try to have actually a lower quantization error, so a lower channel estimation error, and from there you have better performance. If you have B equal 2, B equal 3, B equal 4, you see that the performance increase. In the red one, the performance increase slightly. The blue one is a different type of codebook. The performance increase slightly as well. Ideally, if you want to retrieve the performance of the black one, you would need an infinite number of bits of feedback, which is obviously impossible. So the problem is that as you increase B, you increase the overhead on the feedback. You have a systems where you perform downlink multi-user transmission, but on the uplink, all those users have to report information back to the transmitter, and the overhead is proportional to B. So as you increase B, you consume resources on the uplink for channel state information feedback instead of using this for actually data transmission. And so this is a problem, and it's a problem. The problem is getting worse and worse as you increase NT. So as you increase the number of transmit antennas, you need larger dimensional code books. You need to report more bits of feedback, and this consumes even more the resource on the uplink. And so that's a major problem when you go to massive MIMO, and if you want to apply massive MIMO in FDD, you would really struggle to report the channel back to the transmitter and have it sufficiently accurate, right? That's why there's been a lot of research on this in the past five, a bit more 10 years on massive MIMO and channel estimation and feedback and design of precoders and all those things, because it's a problem in FDD. In TDD, massive MIMO would work better because then you estimate the channels on the uplink, and if you have good channel estimation on the uplink and you have good calibration of the RF chains, then you can use that estimate to design the precoder for the downlink. You will still have channel estimation errors, and some of those channel estimation errors comes from what is called pilot contamination, which is a specific problem when you do channel estimation, right? So this is just to let you know. Now, do we know in information theory the optimal performance? So we know that DPC is capacity achieving when you have perfect CSIT, when we know the channel perfectly. When we don't know the channel perfectly, actually we don't know what is the optimal strategy. So in information theory, we don't know what we need to do. But for those who work on rate splitting in their project, you will find that what we showed is that actually rate splitting is information theoretic optimum when you look at multiplexing gain. So when you look at the slope of the sum rate, for instance, you can show that actually the rate splitting strategy is actually information theoretic optimal. So you cannot get a better slope than what rate splitting achieves. So that's why we know that rate splitting is a good strategy. But really, strictly speaking, to achieve the capacity when you have imperfect CSIT is still unknown. So we have some papers where we show that you can combine DPC and rate splitting into one architecture, and to my knowledge, this is the best strategy that you can come up with so far, but we don't know whether you can do something better than that. Right, so let's move on to massive MIMO. So in massive MIMO, essentially, you're looking at uplink and downlink scenarios, multi-user scenarios. So you're looking at broadcast channels, multi-antenna broadcast channels, multi-antenna multiplex channels. But the big difference is that the number of antennas at the base station is much larger. So instead of having 4, 8, 16, now you go into regimes that are actually much larger, 100 or something like this. What is the benefit there is actually that you have the law of large numbers kick in, which enables you to actually have some relatively simple precoder design and a relatively simple scheduler as well. Now you can imagine massive MIMO very simply. So you have a transmitter where you have many antennas, right? And so you have many receivers. Right, and because you have many antennas here, whenever you create, you're using a precoder, you create a beam essentially, and because you have many antennas, the width of that beam will be quite narrow. So essentially, you create beams that actually gets quite narrow as the number of antennas increases, right? So you can imagine this as kind of pencil beams or kind of laser beams where you aim at focusing all your energy on one user, one specific users. And that beam would be a function of the channel of that specific users, right? Now, because you have very sharp beams, you means actually you use all the transmit power efficiently because you don't spread energy around. This is quite different from a scenarios where you have maybe just two antennas, for instance, and you have two users, right? And so the beam for that user would be quite wide and the beam of the other user would be quite wide. So you would actually quite kind of waste a lot of energy in some other directions when you have a small number of antennas. So here, large number of antennas enable you to actually really focus all your energy to one particular users, and that enables you to have a large array gain, also called beamforming gain. So that's the first benefit. The second benefit is that you have low multi-user interference. If you have very sharp beams here, those beams will not will focus, very specific point in space. And so you will not create, there is very low probability that that beam will also hit another user, right? So that's one benefit. The other benefit is that you can rely on very simple precoder design. So ideally, if you have an infinite number of antennas, what you could do is simply do some form of match beamforming. You only care about the channels of user one. Here for user one, you take user one and you do maximum ratio transmission for that user. For user two, you do maximum ratio transmission for the other user. Now, if you have a finite number of antennas, this is not a good strategy because if you do maximum ratio transmission, you will not get rid of the multi-user interference. In here, if I do maximum ratio transmission here, if I choose WP equal to HP Hermitian, HP Hermitian multiplied by HQ is not necessarily equal to 0, right? So just doing maximum ratio transmission is not a good strategy. But if you have a large number of antennas, HP is very likely to be orthogonal to HQ. And in that case, simply doing maximum rate transmission is actually relatively simple, very simple, and actually would work well. But you need a very large number of antennas. So actually, in practice, you would not really use that. You would typically use zero forcing beamforming, right? Right, but that means actually because you do zero forcing beamforming, and the channels are very likely to be orthogonal to each other, you can actually simplify the scheduler. You may not have to rely as much as you need on greedy scheduler as I did here. So here you see that the gain is quite significant because you need to find users that actually that work well together. So typically it means actually the channels have to be kind of orthogonal to each other. When you go to massive MIMO, because the channels of one user is likely to be orthogonal to the channel of another user by the law of large numbers, I will show you this in a moment, it means actually you can relax the design of the scheduler to some extent, right? So that leads to actually some simpler scheduler as well, simplified scheduler. Now, the main problem is you need a lot of channel state information at the transmitter. So you need to know all those H at the transmitter. Otherwise, you will not have large beamforming gain. You will have a lot of multi-user interference. You will not have a simplified precoders, and you will not have a simplified scheduler, right? So a lot of the burden is put on this, having accurate CSIT. And that puts also burden on calibration of the RF chains and so on, even if you have a TDD system. Right. So what is the intuition behind massive MIMO? Well, it's simply the following one. If you have channels of users, let's say I have a channel of user L and user P. Let's imagine I have a MISO case. So here I have single antenna receivers, and I have IID relay fading channels, right? What's happening is that if I take the channels of one user and I do the inner product with the channels of another user, this inner product is likely to be equal to 0 in the limit where NT is equal to infinity, right? So 1 over NT multiplied by this is actually will tend towards 0 if L is different than P. And so this is good. This is not something you would have if you have a finite number of antennas. If you have only 4 antennas, you can do this on MATLAB. If you have only 4 antennas, this will not be equal to 0. But if the number of antennas increases, this will tend towards 0. And this is very good. That means actually if you take 2 random users and the channels of those 2 users are orthogonal to each other, that means that if you precode your data towards the channels of one user, your precoder will likely be orthogonal to the channels of another user. So if I have lots of antennas here, and I have the channel of user 1 and channel of user 2, and I decide to have W1 to be equal to H1 Hermitian, right? So here, if I do that, H1 Hermitian multiplied by H1, this is good. I will maximize the SNR of user 1 here, right? But here, the stream of user 1, I will have here H1 Hermitian multiplied by H2. So I'm going to have here the receiver something like H1 Hermitian multiplied by H2. And if H1 and H2 are non-orthogonal to each other, this is non-zero. But as NT increases, this term will actually tend towards 0. And so I will have a very small interference that I will experience at user 2. And this is why low precoder can be used in massive MIMO in the limit where you have a really large number of antennas, right? So this comes from the law of large numbers. And so once the law of large numbers kicks in, this is when you can start to benefit from this. And so you need typically a few hundreds of antennas to really have that. So in 5G and 5G new radio, you have typically 64 antennas. So I'm not sure you can really say this is really massive MIMO, but you're going towards that. Now, to do that, obviously, you still need to know the channels of the transmitter, right? But that would enable you to have actually relatively simple precoder. Right, so let me show you a little bit what this means. So let's imagine that I'm doing maximum ratio transmission, or maximum beamforming, so MRT. So I'm transmitting for user S, I'm transmitting along the channels of user S, right? I'm just doing the Hermitian of the channel of user S. And I'm transmitting at a power, I have a certain total power ES available, and I divide by the number of antennas. So each stream gets a certain power level, very small. So what I want to show you here is the benefit in terms of energy efficiency that you can see from here. Let's imagine that you have the SINR of a certain user Q. I'm going to have this term here, and I'm going to have this term here, which is the interference term plus the noise, right? For user Q, you have the chance of user Q, precode of user Q, precode of user P. Now, I have here a transmit power that is ES over NT and ES over NT. I assume that all streams are allocated the same power. And so because of the law of large numbers, this term here, WP, will be proportional to HP Hermitian. And so HP Hermitian will be orthogonal to HQ. So this term divided by NT, this will tend towards 0 as NT increases. So you see that this term here will disappear. And I would have a term here that is such that here I will maximize the signal term here, because I will do a maximum ratio transmission. So this term will be maximized here. So what I will end up with here is actually the SNR of actually a single user transmission that is, so on average, I will have a certain beamforming gain here, right? And I have used only a transmit power that has been divided by the number of transmit antennas. So I've used a very small amount of power for user Q, But because of the beamforming gain here, and because of the fact that I got rid of the interference, this is actually equivalent to the SNR I would have obtained if I had allocated all the available transmit power ES to a single user at a time over a non-fading channel, right? So you see that your SINR in this multi-user scenario is equal to here a long-term SNR of a single user, a single user that would have been allocating the total power ES, right? So this is quite interesting because it shows you that you can achieve the performance, the SNR of actually a single user scenario where you would have allocated all the power to that user, but you do that with by using only a fraction of the power because the power allocated to that user is being divided by NT. And additionally, you transmit to multiple users in parallel, right? So you essentially use a total power that is equal to that. You transmit to K users, and each user will achieve a rate that is the same as if he's alone in the system with a total power allocated to himself, right? So that's where massive MIMO is very useful. In other words, it can scale down the power by a factor of NT, and at the same time, it can have a multiplexing gain that is proportional to the number of users that you scheduled, with K smaller than the number of transmit antennas. But this is always, again, under the assumption that you know the channels perfectly, the transmitter. Right, so how you do this in practice, typically, you would use zero forcing beamforming. And in zero forcing beamforming, here in this term, as the number of antennas increases, typically these terms actually will become more and more diagonal because the channels of the users get orthogonal to each other. So these terms contribute less and less. In the limit where you have a very large number of antennas, essentially you will boil down to something like maximum ratio transmission for each of those users. Right, so let me show you some simulation results here, and then we're gonna have a break. So you have here 4 transmit antennas, and so here you see the performance of 4 transmit antennas. You have the blue one here, the plain line. This is actually an upper bound on the performance. The dashed line here is actually dirty paper coding. This one is zero forcing beamforming, and this one is maximum beamforming, maximum ratio transmission, where you do maximum ratio transmission for each of the users. And you see that this one performs very badly because you're not able to get rid of the multi-user interference, and you have only 4 antennas. Zero forcing works better, but it's still quite far away from DPC, and DPC is further away from an upper bound. So this is the capacity achieving one. This is an upper bound on the capacity. If you increase the number of antenna and you move to 16, for instance, you see that the maximum MBF or maximum ratio transmission increases, but it's still quite far from what you could get here. This here is obtained by doing zero forcing beamforming, DPC, and the upper bound on the capacity. So you see that they all converge towards the same results. So that means actually just doing zero forcing beamforming here, exactly even without any scheduling, you get actually the capacity, right? That would work really well. Maximum beamforming or maximum ratio transmission, you would need to increase the number of antennas to a much larger number in order for it to come closer to this the green performance here. Right, so that's why in practice typically you would use zero forcing beamforming. So that tells you 2 things. It tells you that from the previous simulation, if you have a small number of antennas, but you can afford having some form of good scheduler, then linear precoding like zero forcing is good as long as you have perfect CSIT. Then you combine zero forcing beamforming and scheduling. That's good if you have a low number of antennas. If you have a large number of antennas and you go to the massive MIMO regime, because the channels tends to be more orthogonal to each other, then you don't need to rely that much on scheduling, and zero forcing beamforming would also work really well. So that's the message. So either you have a large number of users and you can do scheduling and pair the good user together, or you have a large number of antennas, much larger than the number of users. In those two extreme scenarios, you actually having simple linear precoding actually would be a good strategy. Under the assumption that we have good and accurate knowledge of the channels at the transmitter. If you have inaccurate channels at the transmitter, the performance of this would drop, right? Can drop quite significantly. If you have mobility, for instance, we have some recent results that are available online, where we show that once you have mobility, then those performance in the massive MIMO regime can drop quite significantly. And then you need to look at other techniques. And so one of them, for instance, could be the rate splitting techniques, or rate splitting multiple access, that would tackle this problem of imperfect channel state information, and would tackle the problem of mobility in massive MIMO, because it would be inherently robust to any form of imperfect CSIT. Right, so let me stop here and for a few minutes, and then I will go into the multicell. Thank you. And if you have any questions, please feel free to ask.
Hello, Bruno.
Yes, hello.
I have a question about the sum rate and the rate of the 1, rate 2, rate 3, and the weight of the rate in that part.
Okay, maybe you refer to that. Here?
Yeah, you're right here. Yeah. It's the rate is the sum rate. The maximum rate is achieved by the sum of the all rate is RS, and you change the weight of the rate. I mean, the rate is depend on the channel state information, right? How can you weight it, or the W is like a power allocation?
No, the W is could be something like we have here. Why is it so slow? So remember what we did here, right? So we had something like this here, right?
Yeah.
Right. So here I'm transmitting on one user at a time, but I'm finding the user that maximizes this ratio.
Yeah.
Okay. Now I'm saying that I may transmit to multiple users at a time, but instead of maximizing this, I maximize now. I may want to maximize a sum over WQRQ. And I want to find maybe a subset with Q belonging to K, right? I may want to find a subset of the users to maximize that, right? So for instance, you have 20 users in the cell. Here, you would look at one user. What is the user, one user that maximizes this for each channel realization, right? Or for each time instant. Here, you would look at what subset of the user I need to transmit to. So for instance, you have 20 users. At time 1, maybe you will transmit to user 2 and 5. That subset would be the one that will maximize this weighted sum rate. At the next time instant, maybe, for instance, user 6, 10, and 11, right? It may change. The number of users you scheduled for each realization may change. That will depend on the number of antennas. If you have 4 antennas and you do zero forcing beamforming, on some channel realization, maybe you will split only 2 users. On some other channels realization, you may split 3 users. Maybe you can split 4 users. But the way you will choose that may depend on the subset that maximize this. Now, those W here, what you could do is to design the WQ here as 1 over RQ bar, right? Based on the proper fair scheduler, right? So each of the user, you will update the long-term rate, right? And then you will find what subset of the users would maximize this weighted sum rate. What you have here is really what you do in 4G multi-user MIMO and in 5G multi-user MIMO.
Okay. Yeah.
Okay, so
yeah.
This is actually more complicated to implement because here you schedule 1 user at a time. This is what you have in the main part of coursework 3. Here, you would need to actually design the precoders. That's the same as in when you do single user transmission. You need to design the precoder, but here is based on zero forcing beamforming. But also you need to find a subset of the users to whom you're gonna transmit to.
Okay.
Right?
Yeah, that's good.
Okay. Any other questions? Anyone? No questions. Okay, let's continue then. Right, so let's move on to the last part because this is also important for your coursework 3. So far, we looked at the case where we have only one transmitter, multiple receivers, or multiple transmitters and 1 receivers, and each of those nodes could have 1 or multiple antennas. Okay, so now in reality, you don't have that, only that. What we looked at, if you like, is a single cell scenario. So you have 1 cell like this, and you have 1 base station that serves multiple users, right? It could be the downlink, could be in the uplink. Now, in reality, you don't have that. You have multiple base stations, multiple cells, multiple users that is actually deployed over multiple cells. And so what's happening is that you don't only have intracell interference. So that means you don't only have interference that comes from maybe among those 2 users that are attached to the same cell, where you transmit information to that user, you actually create interference to that user, but you also have intercell interference. So that user that is served by this base station will actually be exposed to interference coming from the other transmitters, right? So this is what you see here with those green and red lines. This user here will be served by this base station here, but we'll see interference from 2 other base stations, right? So that's going to be the intercell interference or multicell interference. So we're going to start having multiple forms of interference. You're going to have interference between the streams that you transmit to 1 user. If 1 user receives multiple streams from a base station, you're going to have interstream interference. You're going to have multi-user interference because you're going to have interference from multiple users that are located in the same cells. And then you're going to have multi-cell. So this multi-user interference is called also intracell interference, right? And then you're going to have the multi-cell interference, or called intercell interference, that comes from base station that actually other base stations. And the same in the uplink. For instance, if this user want to transmit in the uplink to that base station, then he will see interference from maybe this user that will transmit there as well. So that's going to be intracell interference, but also from other users, from those 2 that wants to transmit to their base station, but the signals is also received at that base stations, right? So that's going to be also intracell and intercell interference. Right, so so the first thing to do when you look at that is to look at your long-term SINR. This is something you will do in coursework 3, and you get a rough idea of what is your long-term SINR when you take into account the interference, the intracell interference that you have in the network. So you drop 1 user, you drop multiple users, you look at each of those users, and what you only take into account is the long-term, the shadowing in the path loss. So you're looking at the signal strength of your desired user, and you look at the interference that would actually come from the transmit power of all those base stations, for instance, here the downlink, and the path loss and shadowing of that user. That gives you a rough estimate of this long-term SNR, and this is the typical deployment, typical what you would have in maybe in a 4G. This is an example of 4G that you would have. I talked about this a little bit at the beginning of these modules, but here what you see is that you have essentially users are mainly located between 0 dB, -5 dB, and 20 dB SNR roughly here. If you have 3D tilt, so you can tilt the antenna arrays at the base station, then that distribution shift to the right slightly. So in your coursework 3, you will have to generate many users across multiple cells like this. I mean, primarily across one cell, but this cell will be exposed to interference from 6 adjacent cells. So you're going to have something like this, but then you're going to have cells like this, and like this. So you're going to have cell 1, 2, 3, 4, 5, 6. We're going to be 6 interfering cells, and you're going to drop many users here in the center cell. And for each of those users, you're going to have to compute that and then plot the distribution. That's going to be the first part. And you're going to have something that is similar to what you have here. Not exactly the same, but similar. Right, so let's look at that. So let's imagine now that I have a scenario where I have KT user, total number of users is KT, distributed in NC cells. And I'm looking here at, let's say, a downlink. But you can do the same in the uplink. I have KI user in cell I. I have a certain number of transmit antennas at the base station I, and I have a certain number of receive antennas at each of the receivers. And so a certain receiver here, receiver vector, observation vector, because I have multiple receive antenna at user Q potentially. I have a MIMO channel matrix for user Q between the antenna I, base station I, and the user Q. And I transmit a signal vector CI prime. So the CI prime essentially would be here, for instance. That's my signal vector that is transmitted by user I, right? And this will actually include data that's intended to that intended user Q, but also other users in that cell. Right. Now I'm corrupted by here intercell interference. So this is what is transmitted by cell J. And I receive this at user Q. So for instance, here, this one would be representative of what I have here by those 2 red lines. I'm going to have 2 interference to that user Q that would be modeled by this term here, right? Now, in this case here, you see, this is also very important to model the path loss and shadowing, because the distance between that user and that base station can be quite different from the distance between that user and that base station, right? A user's here, typically a user would be closer to his own base station than to any interfering base station, right? Right, so if you have linear precoding, so my CI prime now is PI multiplied by CI. CI is now the vector of symbols that I want to transmit to all my users in cell I, and I precode them. And this can be written as a sum over all the users in a subset of the users I want to transmit to. So KI here is the set of users who are actually scaled by user I at a certain time instance. So for instance, I have 10 users in my cell I, and at a certain time instant, I transmit to only 2 users. So in that case, I will have a sum over 2 users of the data intended to user 1 and the data intended to user 2. The data of each of those users will be precoded. I have a precoder here, give me the directions of the precoder, and I have a power location that gives me the power that I allocate to each of those streams of user Q in cell I. Okay, so if I look at that here, let's imagine that here I have 2 users here. I transmit to this one and this one. Maybe I transmit to multiple streams to user 1, maybe to multiple streams here, but I may have other users here as well. But I have decided to select those 2 users among those many users here. and I will transmit to 2 streams here and 2 streams there, assuming I have, for instance, 4 transmit antennas. So user here will see interference from those streams that are transmitted to the other users, but we'll also see interference from those 2 red arrows coming from 2 different transmitters. And those 2 transmitters will transmit information to their respective users. So this one will transmit information to this one will transmit information to this one, but those signals will also be received at the user of interest here, my user Q. Right. So once you have that, then you have a sum here. Then you can actually write your entire system model, your received signal, where what I'm doing is simply I'm taking that and I'm replacing Ci prime by this expression here, right? So now I have this. I have my received observation at user Q is given by this. Those are all the streams that I intended to user Q in cell I. This user Q in cell I will see interference from other streams that are transmitted in cell I. So I'm still in cell I, transmitted from cell I, but those streams are intended to user P that are different from user Q. So this is my intracell interference, right? So this term here, let me write this. This is in red, for instance, this red. No, red was the other one. So let me write this in green. So this is green, right? So what is green here? Green is, oh no, not green. Green is not good. Sorry. Let me take yellow. So this is red. Intracell, intercell is red, and yellow is intracell. So intracell here would be the interference that actually the signal that are transmitted from user to this user that actually create interference that one. So I have here interference to that user, right? So that data intended to that user but create interference to here. So that, and I can have multiple stream of interference here, intracell interference. And I have the red ones are the 2 red ones here. Right. So this is what I have. I have my received signal here. This one, that looks like a point-to-point MIMO. I transmit multiple stream to user Q, and I receive multiple observation. This looks like a point-to-point MIMO, where I pre-code that, those streams of information, but now they have been corrected by intracell interference and intercell interference. Those intercell interference are a function of those precoders that I have for those different streams. Now, if I expand a little bit more, and because I have multiple receive antenna, I can use those multiple observations to do some form of combining. Right? For my stream L, so I want to, for instance, decode stream of you. So I'm going to have a combiner here, 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 and here. Here I have split these terms here.
Bruno, something wrong with your microphone.
Oh, really? Can you hear me?
Yeah.
Okay,
there's some current noise, and then we can hear you.
Okay. So I have stream L of user Q in cell I. And so this is received at user Q and is precoded by a certain precoder for user Q and a combiner for user Q, but in the precoder is designed for stream L and a combiner for stream L. Then I have inter-stream interference, which essentially tells me that I'm still looking at from stream L perspective, but I see interference from other streams that are intended to the same user. So I have the still user Q, but stream M intended to user Q, but M different than L. This is inter-stream interference. I have inter-stream interference because here I'm transmitting multiple stream to that user. And then I have the intracell interference and intercell interference. Now I can design or combiner here. For instance, I can design an MMSC receiver, MMSC combiner, and this MMSC combiner will take care of the interstream interference, the intracell interference, and the intercell interference, right? So you're going to have now a covariance matrix of the interference plus the noise will be essentially a covariance matrix of these terms, of these terms, of these terms, plus the covariance matrix of the noise. And then you can design your MMSC receiver, and this will be done for a given precoder design, a given values of P, right? Now in your coursework 3, this design of P may change. If you have a single user transmission, in coursework 3, if you have the main part of coursework 3, you have single user transmission. You transmit one user at a time. So you may transmit multiple streams. So you're going to have this part here, but you will not have the intracell interference, but you will have intercell interference. That's the main part of coursework 3. But if you go to the bonus question with the zero forcing beamforming, then you will have this interference term, you will have this one, and you may not have this one because I think in that bonus question, we assume that you have single receive antenna. Right, so you will see different scenario. But so depending on your scenario, essentially, you're going to have to write this system model and then design your combiner based on MMSC receiver, for instance, or you do MMSC SIC or something else. In the coursework 3 is based on MMSC. And your precoders here will have to be designed, for instance, based on zero forcing beamforming or based on the code book that you have available in the standard, the code book of precoders. Right, so once you have that, you can compute your SINR. So you can, for each stream of user Q, you design your SINR, which is given by this signal strength divided by your total interference term. So your signal strength is the strength of that signal here, right? And then the total interference will be the interference of this one plus the interference of this one plus the noise, right? So that's why you have many sources of interference here: interstream interference, intracell interference, and intercell interference. Right, so this is how you can design your receiver. If you assume you have MMSC, for instance, you can compute the covariance matrix of each of those interference terms: covariance matrix of the noise, covariance matrix of the intercell interference, covariance matrix of the intracell interference, covariance matrix of the interstream interference. And then you can design your MMSC combiner for the stream L of user Q, for instance, using that. Where your covariance matrix now is given by that. And you can obtain your SINR of that stream L of user Q. Okay, so this is essentially what you're going to have to look at in your coursework 3, but you're going to have to be very careful because in coursework 3, your precoders comes from the codebook. So you're going to have to choose which precoder maximize the rate of user Q. So once you have this, you write the rate of user Q as this, and then you have to find the precoder that maximize that rate. So you're going to have to go over all the precoders in the codebook, find the one that maximize the rate, and this will be the precoder that actually is used for transmission. And then you're going to have the scheduler as well. The scheduler will actually, the proportional fair scheduler will actually identify which user at which time instance should be the one to be scheduled. Okay, so you will see. You will play with the MMSC receiver, you will play with the proportional fair scheduler, you will have to write the whole system model of this multi-user, multi-antenna communication. You're going to play with the code book. You're going to play with changing the number of antennas and the number of users, see the effect on the performance. You will play with the correlation in the channel, see the impact on the performance as well, because the rank, or actually the eigenvalues of those channel matrix here, those H will change. So the number of streams that you will be able to transmit to a given user will change also according to the correlation that you have in the channel, and so on. Right, a very nice coursework. I think very, very useful for you to really understand the whole module. Right, so let me use the 20 minutes left or so just to talk a little bit about some other things. And before going there, maybe Is there any questions on this before I move on? No questions. Okay, so here this is a very light part. I want to discuss about some other things that obviously what we talk about in this module is some of the fundamentals, but there are many more things to do than that, right? So things that in wireless, I mean, nowadays, there's a lot of interest in going beyond just communication. So it's to actually really looking at integrated wireless systems where you use wireless not only for communication, but you use wireless for some other stuff. And so one area is the joint design of wireless information and power transmission. So the joint design of wireless communication, wireless power transfer. And one interesting thing is that wireless power transmission and wireless information transmission were kind of, studied or discovered around the same time by Marconi and by Tesla, right, 100 years ago, more than that. And if you look at wireless communication, it's now in its 5G, right, clearly. If you look at wireless power transmission using radio waves, you could say still in your 0G. So there is not a single standard that does wireless power transmission. What you have is inductive power transfer, which does not use radio waves, which use completely different physical mechanism to transmit power from one node to another node, but that works for very small distances. This is what you have in your phone when you want to charge your phone, for instance, on a patch. Right. Here we're talking about really radio wave transmission of using radio waves transmitting information and energy. But there is an increasing actually interest in this area simply because the power consumption of the electronics decreases and the number of devices explodes. And so you're looking at ways to really make use of radio waves for the dual purpose of communicating and energizing. So this is a big area also that is really motivated by the fact that in the future we'll see a very large number of devices, and those devices will be very low power. Right. This is something we worked quite a bit, and leads to a lot of very interesting problem for communication engineers, which is really trying to understand if you have a certain spectrum, how do you make the best use of that spectrum to convey information and to convey energy at the same time. For instance, you want to convey information to a certain user here. At the same time, you want to use those radio waves to power a certain device. So this would have lots of application in IoT, Internet of Things, for instance. You can imagine in the future, maybe your Wi-Fi router, you will watch video on your phone, and at the same time those radio waves that are used to convey information to your phone will be used to charge I don't know, sensors that you have in your house, right? So the good thing with this is actually it's completely controllable. You can really control your radio waves to charge any device anywhere, but the challenge is to really do it because the power level you can deliver is quite small. Right. So this is something that actually we've been really pioneering in the past few years, and really looking at this from a signal design and processing perspective. How you have to design suitable signals for power transfer, and once you have that, how can you combine with more communication theoretic results to come up with a unified theory of actually transmission of information and power? Very interesting topics. And so you realize actually there is a trade-off between conveying information in terms of rate and conveying energy, which is measured in terms of the amount of DC power that can be delivered to a device. And there is a trade-off between the two. And so you would have to actually change the signal processing or the signal design dynamically, depending on what you want to do, whether you want to do communication or power, or you want to do both at the same time. You can adjust this. And so your whole network could be designed such that at every time instant, you really make use of the radio waves and the spectrum so that you can really go into either power transfer, communication, or something that lies in between. Right, so we have, in normal times, we have a whole lab that is actually working where we have demonstrated this. So this is actually a earlier version of a prototype that does that. We have now a much bigger setup with many more antennas, and we work with Huawei to actually enable wireless power transmission and application in 6G. So what we do is, this is actually a whole system that performs, you have multi-antenna processing. So we design waveforms and multi-antenna processing jointly so that we can deliver information and power, and we perform channel estimation, and those waveform and actually multi-antenna processing change every second, for instance, depending on channel realization. And then the energy is captured by an energy harvester, which is called here rectifier. You can see it here. So this is the circuit, one of the circuit, and this one is another one that is designed to harvest energy. And so what we do there is really measure the amount of energy that can be delivered depending on the signal strategy that we used. And we looked at the trade-off between communication and power transfer. Right, some other stuff that obviously is popular is to use also learning techniques, so machine learning techniques in communication and could be in power transfer. And so this is an example of what you can do. So, typically in communication, we use a lot of signal processing and optimization and of course, information theory to try to identify what's the best communication strategy that we can come up with. And so here what we do is actually use machine learning techniques to try to learn good modulation when we do a joint design of communication power transfer. And so for instance here, the first figure here is actually a 16 QAM constellation that is obtained by doing machine learning techniques. When we don't care much about power transfer, we care more about communication. And so what you see that you get 16 points that are roughly spread, kind of uniformly. You try to maximize the distance between those points. So this is a little bit like a QAM. It's not exactly a QAM, but would have the similar performance to a QAM, where you really try to maximize the distance between the points. What you see here on all those graphs is actually how this modulation would actually change as you want to deliver more energy to a receiver. So you see that here you have the delivered power is increasing. And so what's happening is actually as we increase the delivered power, as we want to deliver more power, the modulation changes. You see that actually the points disappears here. That means actually some points collapse onto the same, becomes the same, so they merge. And so that means that actually, if you want to do communication or if you want to do energy transfer, the modulation should be different. So this is very important. That leads you to a very fundamental question: is modulation good or bad for communication and power transfer? And so there is a trade-off even in the design of the modulation. So if you change the modulation, you have to change the waveform. The coding may change as well, the receiver designs, and so the entire physical layer of actually communication network may change if you want to really make the best use of radio waves for communication power. So this is an example of where actually machine learning can be used to learn those modulations, because it's not easy to do with sometimes with classical optimization tools, simply because it's highly nonlinear. So actually the way we model this, there is a lot of nonlinearity. For those doing projects, MSc project on wireless power transfer and wireless information power transfer, you will know what I mean by nonlinearity. Right. So this is an example. Now, other things that actually obviously we looked at in the context of research now for 6G is one aspect is obviously enhance of 5G. And so in 5G you have three main pillars. The first one is called EMBB. So this is really mobile broadband. That means try to deliver high throughput to many users. This has been really the main driver in 4G, right? But in 5G, we have beyond that, and massive MIMO is one of the techniques. Millimeter wave is not the technique. So going to higher frequency, this is really to tackle this millimeter mobile broadband. So E stands for enhanced. URLLC, so this is ultra reliable low latency. So this is really low latency communication that needs some high reliability. And this can have application, for instance, in remote surgery. You want to, you have a surgeon in I don't know, in London doing some remote surgery of a patient that is somewhere else in the world, and you have to make sure that actually the latency is as small as possible over the network, because otherwise you can imagine, you know, it could be quite catastrophic. So you have a lot of application that requires high reliability and low latency. Another one could be autonomous driving. Right, so you need their low latency communication, because when you drive and the car have to communicate with each other, obviously, if there is any form of latency that is non-negligible, then that can lead to also major problems. And the last one was machine type communication. So this is really more for factories application or Internet of Things, where you have an exploding number of devices. Devices could be relatively small. They don't have really huge amount of data, not like the eMBB. So we're not talking about device that would actually stream movies, but you can have maybe many devices, but they need a low data applications. So this is discussed as part of machine type communication. Now in 6G, you can imagine those three pillars will remain there, and there will be new techniques that have to be designed to enhance those techniques. But you can have other services as well. So one of them I mentioned is the wireless information and power transmission. So you use wireless to do two things at the same time. Something else could be integrated sensing and communication. So you have also, some of you may do a project with me on integrated radar and communication. So this goes along those lines. How you use the wireless, the spectrum, to actually do multiple things at the same time, here radar and communications. And so the problem here is that you're going to have big interference between communication and radar. And the question is how you can manage this interference in a suitable manner. How you design waveforms that are generally for communication radar. How you do multi-antenna processing for communication radar sensing, and so on. Lots of activities on new materials and new surfaces. Metamaterials are very popular. This changed actually the design of some of the antennas, and there is a nice interplay between communication theoretic problems and antenna design or surface. Lots of new reflecting surfaces, actually intelligence, where you try to actually change the wireless channel and try to enhance the performance by doing so, and having kind of passive surface that you put on the wall, but you can control them. And that would actually be very useful if you want to actually do, for instance, massive MIMO, but you don't want to have active antennas or having RF chains for each of those antennas. You may have some of those antennas actually will be completely passive. New multi-antenna techniques beyond massive MIMO, new multiple access techniques. I talked about the rate splitting before. That can be used to really unify all the existing multiple access that we have. So the multi-user MIMO is also called sometimes space division multiple access, which is a particular way of actually managing the interference. There are other techniques like non-orthogonal multiple access I talked about earlier on, and you have other techniques like the one that some of you work on, which is rate splitting, that actually unified all those techniques into one framework. And because the framework is more general, the performance are enhanced. And so you can also look at benefits of combination of those different techniques. So for instance, rate splitting can be used to tackle some problem in massive MIMO, could be used to tackle some problem in intelligent surfaces, in radar and sensing, and so on. Okay, and many other things. So I think I will stop here with this lecture. I hope you enjoyed it. Feel free to contact me, obviously, in the coming weeks. when you work on your coursework 3. If you have any questions, feel free to contact me or to contact the GTAs, Longfei and Yang. And feel free to talk to me in the future as well if you're interested in any research in the area of communication, wireless communication, and wireless signal processing, and we'll be happy to talk about that. Otherwise, that's it for today. So if you have any other questions, I will be happy to answer.
Hi, Professor.
Hello.
Hi, can I have a quick question on the zero forcing beamforming?
Yes.
At page 192. So while we have uniformly allocating the power across all user streams, I think we could have the water filling algorithm to allocate power to achieve the sample rate.
That's right. So I have not talked about this, but that's what you could do. So what you could do here, we do that. So in this problem here, you have the SNR. The SNR here is a function of the power that you allocate to each of those streams, right? And so what you see here is that this is a sum rate maximization problem, and then you have a power constraint that you have to satisfy. So you have a power for stream 1, power for stream 2, power for stream 3, and the sum of those power should be constrained. So this is a maximizing a sum rate where you don't have interference between the users, and you subject to a power constraint, some power constraint. This is actually exactly the same power. It's the same problem as what we have in the point-to-point MIMO. And so you could do water filling. So in the simulation I showed you, very often I use uniform power allocation, but it's not the only way of doing it. What you could do is you could design the power allocation using water filling. And strictly speaking, in here, this here means zero forcing beamforming with water filling power allocation, right? So actually, this black line is not zero forcing beamforming with uniform power allocation, is zero forcing beamforming with water filling. But the gap is not so significant, so that's why I have not talked about it. But you're right, you could do that. Now, in practice, the water filling is not used. Typically, what is used is uniform power allocation. So if you have 20 users and you schedule, for instance, 4 users, then you would split the power uniformly among those 4 users. If you have 3 users, you will split them uniformly among 3 users. But you're right, you could use water filling power allocation.
Is it due to the computational complexity or something else why we use uniformly, not the water filling?
Well, it's related to computational complexity as well, but in practice, the problem is, so if you do scheduling, if you do scheduling, you do a form of water filling already, in the sense that what you do is when you schedule users, when you decide to, let's say you have 20 users and you schedule, let's say 3 out of 4 out of 20, and you have 4 antennas. So what that means is that you may not always schedule, let's say you have 4 antennas, you may not always schedule 4 users. You may schedule a subset of 4 users. But by adjusting that subset, you will essentially do a form of water filling. You will actually change the power allocation to each of those streams depending on the number of users you schedule. So it's kind of quantized water filling, if you like. It's not a continuous water filling. It's quantized in the sense that it's the same in single user MIMO, point-to-point MIMO that you do in coursework 3. You will see that you will transmit the full power to one stream, or actually half power for each streams, or third P over 3 for 3 streams, P over 4 for 4 streams. For instance, if you have all the way to 4 receive antennas, right? So it means that you can have 1 stream at power P, 2 streams at P over 2, 3 stream at P over 3, or 4 stream at P over 4. And this is, you can view this as a form of quantized water filling, where you see what I mean by quantized. Quantized means here that you don't allowed to have all continuous power allocation possible, but you have something that is in between. It makes just the life much simpler. And the performance is quite close to doing pure water filling. Right. But if you want to write it rigorously and to maximize your sum rate of the zero forcing beamforming, then you can use the water filling. That would maximize the power. That would maximize the sum rate of the zero forcing.
Okay, so they didn't have much difference.
Yeah, the difference is not significant.
Oh, okay, it makes sense. Okay.
The difference is not significant. There is a difference, but it's not that significant, and so it also leads to more complex implementation and so on, and so that's why in practice is not used. But in the academic literature, it's heavily used, right? It's heavily used.
Thank you.
Any other questions?